I'm here to talk about Caffe and Jupyter and Pandas and a bunch of other stuff, and it's not rocket science. Well, sort of. I actually work for a company that actually does space stuff. So we actually do space stuff. My name is Katherine Scott. I'm a senior software engineer at Planet. You can find me on the internet. All right, so quick overview and background. I do all sorts of different stuff, generally in the domains of computer vision, robotics, and machine learning. Started a couple startups, went to grad school, all those fun things. After a stint of fun employment, I decided to take a job at Planet. And so you walk in the door and you say, cool, new job, where can I help? What do you guys need? And this talk is about the tools and also the process I have of sort of building up a code base to do something interesting. And this is all intentionally imperfect because things do not emerge into the world fully formed and perfect. You build something, you keep building on it, you maintain it, you work on it. This is the nature of software engineering. It is not a perfect thing. And I feel like seeing these sorts of processes and seeing how people build stuff and what they think like when they go do something is really, really helpful. Anyway, the quick takeaways from this talk is that a lot of machine learning is just sorting and moving data around to get it all ready to go. Getting good, clean, prepared data for your machine learning is actually as big of a problem as figuring out like what the right model is to use and how you're going to deploy it. The ML stuff is kind of hard, but it's not that bad anymore. A lot of stuff is turnkey. Like if you've never sat down with like scikit-learn, it's super easy. You don't really have to know how things work under the hood. And then just the general takeaway from all this is automate and analyze everything. Okay, so I have an employer. And their name is Planet. And what do? They have the largest privately held fleet of imaging satellites in the world. We have somewhere, depends on what day it is, 60-something satellites up right now. And they are flying around right now looking at all over the planet, looking for interesting stuff going on and imaging the globe. Soon we'll be actually doing this every day. The entire planet we will be imaging every day and making a giant map at a reasonable resolution. Which means we also have like big capital B data problems, whatever that exactly means. So the final product looks like this. So here is us in San Francisco, and I can actually go and see, this is from the 17th, so I can actually zoom in here, and I can look at satellite photos that came from a satellite and see exactly what San Francisco looks like. So we can actually zoom in here on PyBay. We can go, you have to make the sound effect, enhance. Ooh, so I think we are like we're somewhere in here, kind of? Up. Anyway. Now, this is the product that we make. This is how we sort of deliver the product to customers. Oops, I'm not used to working in full screen. If you guys are really, really interested in this data, we actually we put a lot of it up in Creative Commons, especially all of California. So if you want to go home and actually look at this stuff and play with it yourselves, we have open California data sets. So you can actually go and see California every day. There's some really interesting wildfires going on right now. So if you want to go take a look at that or whatever, just get familiar with it. It's totally open. We're also hiring. It's a great place to work. Let's put that in there. So anyway, when we image, we have one huge Achilles heel. And that is we keep putting clouds in our cloud all the time. So this is a shot of some of our satellites being deployed from the ISS. And I point this out because if you look in this general area, right, it's all clouds. 40% of the Earth's surface, land surface, is covered by clouds every day. So we can't sell that. And on top of that, there's certain areas that are just like continually cloudy. Like the Congo is continually cloudy. Parts of South America are also continually cloudy. I've heard rumors that there are parts of the Congo that have actually never been imaged from space. It's so cloudy, but I don't know if that's true. Each of our images is huge. It's 6600 by 4400 generally as a TIFF, which is what you use if you're doing GIS stuff. That means they're big to store, costly to store, big to process, costly to process. So that means that getting rid of these clouds that we can't sell would save us a lot of money and make for very, very happy customers. So let's look at like the scope of the problem. So I have an app at work, and I can actually see everything coming down from the satellites as it comes down, which is the coolest thing. But this is what like a day in the life looks like. This is a chunk of Quebec, and you can see like, oh, this is great, this is okay, and then there's just lots of these clouds. They're like They're harshing my mellow. I can't sell these. I need to get rid of them. We also, just for reference, we have 2 different kinds of products. So we have basically a full RGB frame, and then we have a NIR RGB frame, which NIR data is super important. We use that to, NIR, I mean near IR. We use that actually to do metrics on like how well farms are doing. So a lot of our agriculture customers use that. So left is our older RGB product, the right is our NIR RGB product. We also have a 3rd constellation of satellites, which is a push-broom sensor, but I'm not going to talk about those in this talk. And so we do this thing called agile aerospace, where we keep sending up different sets of satellites. So the sensors actually change every day. So we get lots and lots of different kinds of sensors. So I basically need to be able to make something that can sort out these clouds as fast as possible, that's reasonably flexible and updatable based on what we're doing. So why don't we get to the meat of our problem, what our image processing pipeline looks like. So satellites are flying around in the air. We have ground stations all over the world. They beam down their stuff. It comes into an ingester. And then we basically do something we call flat fielding. So flat fielding is handling color correction. I like to call flat fielding de-Instagramming. You know, when you take the Instagram filter and it puts like this sort of blackish edge around your image, like an old camera, that's called vignetting. Basically, we eliminate that from the satellites. We also calculate some metrics about them. Once we've accomplished that task, we do something called rectification, where we take the image as we get it down, we have some rough telemetry, and we go and we take a base map. It's just a map somebody's generated who actually has ground truth. That's where the phrase ground truth actually comes from. And we take that map and we go, and we like kind of move it around and perturb it and like slide it around and warp it until it actually fits the ground model that we have. And this is actually extremely expensive to compute. So if we can avoid computing this, we win. Once that's done, we basically send this out to our product team, and they do some image quality control. They make it into nice little tiles that we can sell, and they expose the results to customers. We also have another group that does mosaicing, which is taking a bunch of these, stick them all together into giant maps. So we just did like a giant map of Mexico, like the entire thing at super high resolution. It's super cool. So how do I get rid of clouds? So the first thing I need to say is I'm not just getting rid of clouds. I actually have a 4-class problem, which is I need to get rid of clouds. I need to get rid of water, because we can't sell water. I need to get rid of some sort of one-off scenes that we do for telemetry. So like sometimes we point at the moon and the stars to figure out where we are, and we beam images back, but we don't really need them, but they go into our pipeline. And then I need the good images. I need the things that we can actually sell. So all this means that I need to make a very, very high accuracy image classifier, and I probably want some capability to adjust like how I handle false positives and false negatives. And that it should be reasonably computationally quick. Much, much quicker than the thing that I'm trying to prevent happening. The other things that I sort of need to make this all happen is I need a tool to Turk our data. And by Turk, I mean, how do we actually generate the data set that we train our neural nets on? I also need some tools to evaluate that data before it goes in, because garbage in, garbage out. If I give the classifier garbage, it's going to give me garbage. I also need some tooling to perform the neural net training and just to set everything up. And I need a very standardized way to evaluate the training performance. And finally, I just need a really quick way to deploy and deploy these sort of new models to production. And finally, a feedback mechanism so that when I do screw up, I can handle it gracefully and be very nice about it. So, you know, I come into a new job, it's like, what are the tools that I have at my disposal to make something like this happen? And who went to the Flask talk this week? Who went to the Elasticsearch talk? Okay, let's see, what else is there? I think there was an image processing talk, right? All right, so these are the tools that I use every day to put this stuff together, right? We have like a large S3 storage system. It's basically Postgres on the back end. We also attach a JSON pile of metadata in that Postgres server, or in that Postgres DB. And then we index that on Elasticsearch. I have an existing Flask server, which is basically, it's like an ELK stack, which is Elasticsearch, Kibana, Logstash. So we use that for a lot of our metrics, and I can kind of hack on that to do whatever I want. We have an internal Django server that we use to show all of our scenes internally. And then we have some other stuff that we use, like a tile server to send out JPEGs. And I also get as much EC2 time as I want and some really, really friendly site reliability engineers. All right, so step one. You want to train a classifier. You have to make, if you're going to do this, we have to do it the San Francisco way. We have to make artisanal data by hand. I can't go and download this stuff off the internet, unfortunately. I have to go make artisanal data. So it looks like this, right? So hopefully, oh, no. There we go. So first thing I did is I have to make data. So I go and actually, hopefully this connects through my VPN, stand up a quick little Flask server to go through all the images that I have and start allowing me to like click on a certain image and say, this is water, this is clouds, this is good, this is not good. Oops. And if it'll come up, I'll show you. But it ends up looking like this. And you can go through really, really quickly and click on all these images and say, these are good, these are bad, these are not, these go into this class, these go into this class. And this is really, really simple. We basically filter on that Elasticsearch metadata, and then we just render it out. It's just Flask, Elasticsearch, Ginger templates, and some JS. It's not the prettiest bit of code, but it's acceptable for team level usage and acceptable for some of the employees that I have that actually go and sort this data, and it works quite well. So let's just take a look at what like a little bit of a Flask server to do this would look like. So here's straight up code from that Flask server, and I have a little function here called get validated scene candidates, and I basically have an Elasticsearch wrapper right here. Ooh, let's see what we can do. Control plus. Oh yeah, how's that? Yeah. So we can go in there, we can get the client. I get a list of my satellites. I randomly pick a satellite. I say, give it some conditions. I want scenes that have already been labeled good. This is a little bit newer version. Before that, I was actually filtering out some stuff that we know that the scenes might be good, like the fact that they actually rectified. And then I just return that list. And then I just create a simple Flask route. I say, hey, Flask route, show me some images. And if I hit this with, say, show me bad images, it goes down here, pulls down a list of bad images, and then tosses them to a template, and there's some JavaScript in here that on the post request just basically flags them. Oops. It's one of those days. All right, so I do that. Here we go. I do that. I give this to a Turk. I actually have an employee. His name's Chad. He actually will sit here and actually click through thousands of images for me to help us build up our data set. So Chad goes to work. You know, I come back a couple days later because I made it fairly quick for him to do his job. And I have a bunch of data that I can use. So the next step, after I have all this data, is I need to assemble it and check that it's actually good. Because Chad gets a little tired. Sometimes he does stuff late at night. He might pop open a beer or something, I think. And so we just want to make sure that everything looks and jives and is correct. And to do this, what I've done is I've basically built this Python class that I wrap all of these data munging, moving, collecting applications together. So I can either, run them in a notebook if it's useful, or I can run them in a standalone shell if I need to, if they're a long-running job where it might take a couple hours. And I basically put all the tools I'm going to use in one class, and then I use that class to go build all the bits and pieces of this pipeline. And underneath of all that, I've decided to represent all the data as just a pandas data frame. That means that my data sets are just CSVs. I can use them in Excel if I was really having a bad day. I can play with them, and it's wonderful. And it's fairly lightweight, too, because I'm just looking at the names of the individual images and maybe a tag that's like a short string. Oh, and the last little bit of this is I was slightly clever about how I did this. So all of the underlying functionality gets run through Python multiprocessing. So if I'm on a big machine and I have multiple cores and everything is sort of in parallel, I can immediately parallelize all these jobs. So why don't we take a look at what this actually looks like on the inside. So I have this function called generate dataset, and all I do is I hand it the name of the scenes I want that have been tagged, tell it where it's going to look, what kind of imagery I'm searching for, what tag to look at, and maybe give it a bound on how many images I need. I pull in this client code, and I create a new pandas data frame. And then for each of the types of scenes I need, I basically create an Elasticsearch filter and get the names of scenes. So you see here, hey, I need ones where there exists a particular tag, and the class name is equal to this tag, and it's an RGB image. And then for each of my classes of images, I go through and I say, give me all the scenes. And for each scene, I pull down its data from our basically Postgres servers, and I append it to the pandas data frame. And that's it. So now basically this thing is going through and it's saying, okay, I'm going to query everything, and then I'm just going to shove it into a CSV for you real quickly. It also means that my code to actually generate this and run this and get a CSV is 5 lines of code, which I think is amazing. Like I say, here's the file name, create this class, here are the classes, generate the data set, and save it. That's it. And so now that I've done that, I can actually go and look at all this data in my notebook and play with it and make sure I'm happy with it. So here I am. I'm going to read in the CSV that I generated with that script before and just sort of display it. And so you can see it here. We have this sort of hash for all our scene names. You can see the latitude, the longitude, the time it was taken, what satellite it came from, and some other sort of variables that I have sitting around. And so since this is all Pandas data frame, it works seamlessly with Bokeh. So I can start doing some cool stuff like, hey, I want to make sure that I'm getting a reasonable distribution of scenes across all our satellites. So I go like this, and all of a sudden everything is generated, and I can say like, oh, so for these classes of satellites, I actually have way too much data. For these satellites over here, I might be slightly data deficient, and maybe I should go and try to actually round that out in terms of my data set. Similarly, I can look at the distribution of, say, like tag classes per satellite to make sure like one satellite isn't just getting bad images all the time or just getting cloudy images. We want like a uniform distribution across them. So that ends up looking like this, right? And this is, with Bokeh, this is 2 lines of code, which is just incredible. I just tell it what fields I want inside of that CSV file, and it renders it for me, which blows my mind. Have you guys ever played with Matplotlib? It can be a little futzy. Like, this is awesome. And then you can start going real crazy, right? So you can start, I have the GPS locate, or I have the latitude and longitude of all the satellites. I know what they've been labeled. I know how to get at my tile server to see what they look like. I can get a little bit fancier, right? So I can say, hey, I'm going to break all this stuff up into individual classes and sort of aggregate the data, like the latitudes and the longitudes, and what sat it comes from. And I can plot it on a Google map, which allows me to actually make sure that I'm getting the whole Earth quite well, and I can show it by scene. So I wrote a little bit of code. You execute this. Now, this doesn't render all that great in Jupyter, but we can go like this. Wonderful. I now know exactly where all my scenes are coming from. I can make sure that I have a really good distribution. And I actually can go in and see what all of these scenes look like even before I start training my neural nets. Make sure everything's good. OK. So I'm happy with this data. Are you guys happy with this data? Yes? OK. So it's time to get it ready for Caffe. Right now, I'm using Caffe. I'm not going to debate the merits of one particular system over another. I really actually don't care that much. I just care that the job gets done correctly. And whatever you're going to use, you go and figure out how to get it set up correctly for your system. So I use, right now, I use EC2 instances, GPU EC2 instances. So make sure you have all your setup Ansible and that kind of stuff ready to go. So we're having awesome SREs comes in. And then the actual preparation of your data and cleaning up your data is not that big. So what do you do when you want to go train something? Well, you randomize, and I think you guys have probably seen this from the other talks. You sort of randomize and split up your data into a train and test set. You assemble all the data. In my case, since these are images, I need to pre-process them, which means I need to scale them down. And I might have to do some other image manipulation on them. And then particularly, one particular thing of Caffe is that it uses an image database. So basically, I take those images, I do all my mucking around with them, and I shove them in this thing called LMDB. So get that done. You also need to generate an image mean, which is just another particular Caffe normalization thing. And then you have to generate all the configuration files that you would send to Caffe. These are basically your base net that may have been pre-trained, your sort of particulars for your application, and then the solver file, which sort of defines your learn rate, where you want to put stuff, how long it should run, and all these different parameters. And you want to do this all in the smartest way possible. So we use roughly this pattern in all our big training class. So I have this internal method, right, called do get raw data. And all this thing does is it says, given some configuration things, which is the destination of where I want to put stuff, I set that path. And given a scene I want to download that scene. And do all the sort of wrangling of handling the work with the tile server. And then here in my main method, and my actual access method, all I say is get the raw data and push it into this path, making sure you do all the stuff that I think you should do. And what it does is it creates that path, checks that directory, goes through our pandas data frame and extracts all the scenes that it's supposed to look for, creates like a little dictionary, and then calls the method above automatically, if I've set the number of cores, through Python multiprocessing pool. So that means I just like for free get multi-core support on this, which means all these images, instead of downloading them serially, they now can get downloaded in parallel, which means I don't have to wait 4 hours. I can only wait like, 30 minutes to get my data all ready, which is really helpful. So this means that once I kind of do this, and I use the same pattern over and over again as I build up this class and all these sort of functionalities that you would use to build this training system. And it means that like to actually get ready to do a training session for this neural net is maybe 50 lines of Python. All I'm doing is setting some loggers, setting some paths on where all the data is going to go, creating this class and passing it in the CSV file that I had created before, and then calling all these methods, which is, get the raw data, process the data, shuffle the data, split the data, save the results, build the config files given the configuration that I want, move all the data here into the image database, calculate the image means, and then you're basically ready to go. And at the very end, the cherry on the top is that I take all of this data, all these data files that I use, all these sort of intermediary things, create like a JSON file that says this is where everything was when I ran this experiment, archive the data. So now I actually have some traceability into how I trained the neural net too. Like what was the data set, what did we do, how did we get to where we are? And that's it. And I run this, and it's ready to go. And so I go into my EC2 instance, and at that point I just have a little shell script, and I say, start training Caffe. So once I do this, it's basically sit around and wait, because it does take a while to train a neural net when you have 40,000 images. So it usually takes about 48 hours. And we've been working lately with this SqueezeNet, which is a sparse dense network trained on ImageNet. ImageNet is a very, very large set of like 1 million different images that have all been labeled. And a lot of the computer vision neural nets basically are trained on this set as they're sort of like lower level things. And basically when I'm doing my training, I'm just basically tuning that network to my particular application. But these guys, they do this, basically sparse dense, so they have these very, very wide nets at the top. They have very, very like a set of smaller nets in the bottom, and then a wider set of nets at the bottom. It came out, I think they released this 5 or 6 months ago. Phenomenal. I've seen basically, I think the size of the trained net is dropped by about 2 orders of magnitude, and the processing time is sped up about 2 orders of magnitude. So if you're looking for a net that you want to play with, highly advocate for this. So anyway, this did require a little bit of futzing with the hyperparameters initially, but now that I think I have a very good set, I have this very turnkey sort of solution to going and training our images. And yeah, 48 hours. All right, so I sit there. A lot of times I run this on Friday, and I come in on Monday morning, and I'm like, okay, how'd we do? All right, so this thing runs. And as soon as it's done, I run another little script using that big class, and I say, take all your training data and all your testing data, run it, grab your classifier, and run your data through it, and label it as you would if it were naive to you. And that way I can actually go and see, I get all the data, all my test data ready to go, and I can see how it performed. And that means I can then generate another CSV file, or actually just relabel the CSV file that I had before, and I can import it back into my Jupyter Notebook and use Bokeh to see if I actually performed as well as I would like. So I went and did that, and that ends up looking like this. And here you can see here the new updated label, or sorry, up over here, the new updated label, the group that it's in, whether it's test or train. And also keep some parameters about the runtime, how long it took to process each individual images, just so I can get some stats. Like is it taking longer to train stuff? Is it taking less time? And then I can go and evaluate the results. So in this little set of functions here, right, a couple lines in an IPython notebook, I look through my data set. The way I've defined this problem is that I set it up so it's a 2-class problem when I actually report numbers, such that true positives are good. Good images labeled as good. True negatives are anything else that was good that got labeled as a true negative. So you have a good scene and it says it's water. And then false positives and false negatives come from that. screwed that up. A true negative is a water scene that was labeled water or a cloud scene that was labeled clouds. And basically, I go through here, write a little bit of code to go through this CSV file and set all the labels. And from that, I can generate all my sort of statistics. So I can do my accuracy, my F1 score, my precision, my false negative rate, my false positive rate, and I get all that stuff ready. And I can also generate my confusion matrix. And if you guys aren't familiar with the confusion matrix, what it effectively is when you have a multi-class classification problem, it tells you what image is getting confused with what other kind of image. And it's really, really helpful for debugging what's going on. So let's take a look at what that looks like. Oops. Huh? Oh, it's live. I probably didn't hit up here. There we go. Okay, so I can see here, right, in just my test set, these up here on this corner are going to be true positives. These are going to be true negatives. Here's my false positives, and here's my false negatives. Or sorry, these are my false positives. These are my false negatives. I actually go and calculate the false negative rate on this training session. This was an early one. We have 11% false negative rate, and we have a 3.6% false positive rate. We have an accuracy, which gives us an overall accuracy of 94%. We actually are doing a lot higher in production. And then my F1 and my precision scores. But where this really actually gets interesting is looking at the confusion matrix, because that allows me to sort of debug where my neural net is having problems and getting caught up. So I go and just do a little quick bit of work here in Bokeh, and I say, take this confusion matrix, do some stuff to color it based on the weighting in there, and then just basically render it out with some floating tags. And that ends up looking like this. And this is really, really helpful. So what you can see here is basically on one axis a set of tags. And this is the axis of like what something was labeled by the Turk. And then the other axis is what it was labeled by the neural net. And for most of the scenes, right, they're correct. So you have 122 bad scenes that were actually labeled bad. You have 916 scenes that were clouds that were actually labeled clouds. But I can actually go in here and say, like, well, how many bad scenes did I have that were actually labeled clouds? Or the one that we have problems with is, you know, how many, let's say, how many water scenes were actually labeled as good? And you can actually sit there and figure out where your problems are living a little bit. And if you want to sort of adjust weightings afterwards to fix some of these things, it makes it really interesting and a really handy way of figuring that stuff out. And if you want to start drilling down into this a little bit more, it's fairly trivial. I can use Pandas again to go and actually sort through these labels and find the scenes that, hey, they weren't working as well as we thought they would from this confusion matrix. And I can go and grab those images and see what they look like. So I got a bit of code to do that here. And now I can basically say, hey, show me scenes that were supposed to be good that were actually labeled as water. And I can debug what was going on. So like, here we go. So this one looks like it might actually be Brazilian rainforest. This one has this little corner case, right? Because we've said, hey, this is a good scene, but the neural net said it's water. Why did it say it was water? Well, this is mainly water, except, hey, we got this corner case of a little bit of land coming in. And we can kind of see, like, this is the same thing. Oh, and we're having some problems with Brazil. So we are actually able to intuit what's kind of going wrong with our neural net, which means that I probably should go back and find more scenes from Brazil and start pushing them into the neural net. And maybe I need to add another class for things that are over water, or I need to look at our telemetry a little bit stronger before I sort these things out. And so I can actually go through, and this is basically what I do on Monday morning. I say, like, what's going on? So once I've kind of gone through that, I may go through this process once or twice before I deploy something. Packaging actually gets really, really simple, because the packaging is taking basically our trained nets along with just the tiniest bit of like metadata, which is basically what how you map the classes to the names that are in there and what order they come in. And all I do is I have another method in there that zips all this up into a single zip file that I give a version number to. And I push that up to an S3 bucket. Once that's up on the S3 bucket, I go into my source and I bump the version number in my source. And all of a sudden, it'll just take that, once that's pushed through to production, it will just start downloading that neural net and using that neural net actually for sorting all our images out in our main image processing pipeline. So what does that look like? So this, again, bit of code. I mean, this is all boilerplate at this point. Set up my logging, build this class again, and pass in my data set, and say, use this number of cores, even though it actually doesn't even need to use those. Pass in a state variable that sort of keeps track of where stuff is, name everything, set the net information, and then make this zip file. And that zip file is what I toss up on S3. And so what does this look like when it runs? So we have this massive job system. It's basically a Python job runner. It runs on EC2. The deployment code for this is effectively 400 lines of Python. All those lines are doing is, most of it is actually just making sure that if it's a new instance of a job runner, that all of those nets are in place and that they're ready to go and that their MD5 sums check out, and then scaling and preparing the image for deployment. And doing color correction, all that sort of stuff. Once it's actually, we run the classification, we then take what we found and we assign it, we assign a label on the image's metadata saying, we think this image is like this, and we basically gate the next step of our image processing pipeline based on this and a few other variables. And so, now it's running. It's 94%, 95% effective. You're going to have a few scenes that pass through. And it's sort of one of these things where all bugs are shallow with enough eyes. So at Planet, we actually have this internal tool that we actually look at all the scenes as they're coming in, or a good deal of them. And so I went to this tool, and it's just a Django server, or just a Django app. And I went and added a button such that users can actually report this data. And when you're training these things, it's actually really, really nice to get the cases where things fail. Like, I can take thousands and thousands and thousands of scenes of water, and they're all going to look the same. What's really important is the 1 in 1,000 scenes of water that looks like the Amazon rainforest that I want the neural net to learn about. And when that happens, somebody catches it. And so I give them a tool to basically go and do this. So hopefully, So this is what it actually looks like live. And so this is what we see when we're actually working. And I see, oh, this scene was labeled water, and it's actually got these islands up here. So what I do is I just added a couple lines up here to say, hey, take this scene and classify it. And this goes to another app that is actually just very, very similar to that original Flask app that I had that allows you to click on a button and say, label this scene like this, and shove its data back into our Postgres servers. And my VPN is slow. And once you close that loop sort of as a bit of process, you can do this continually, right? So not only are we having like our machine learning sorting images, it's actually getting better over time. We actually have new deployments of satellites that are reaching to higher latitudes than we've ever had before. So I actually have data that I've never seen before. But just as a matter of course, I have people, when something is incorrect, tagging that data and adding it to my data set. And since this is all sort of automated and relatively easy to run through, I can actually train and improve the neural nets over time. And we could actually get to a point, if we wanted to sort of set thresholds on performance, where we could just have this happen completely automatedly, in a completely automated fashion. That is to say, it learns more and more about the scenes it sees as people sort of find scenes that don't work and work with the classes. And so that's what the feedback mechanism looks like if it were to load. Yeah, and that's the process that we run through. You guys have questions? I know. I know I just dumped a bunch of stuff on you, so like I can clarify a lot. You probably should come up to the mic if you have questions. Just
please come up to the mic if you have questions. So.
This might be a very broad question. How does Caffe differ from, say, scikit-learn?
Well, so we're actually doing a convolutional neural net. Like in scikit-learn, I think there's some packages now, but like I personally use scikit-learn for like, a KNN or an SVM, a support vector machine, k-nearest neighbor classifier, or like a a naive Bayes classifier. And like scikit-learn is awesome for that. Like it is the toolbox. It is wonderful at what it does. If you've never played with scikit-learn, go home, get some data, do it. It's awesome.
So I had a question. So it seemed like most of the stuff had to do with using image data to process other image data, but the satellites themselves, and you mentioned telemetry, there was just one point in there, like the satellite knows where it is in space, or you guys can infer where it is based on certain positional data. Is that applied at all, so you don't have to guess, is this water? We know
So-
generally it was already pointing at water, and that could help feed the algorithm so you wouldn't get like it's the...
So the way we've structured this, because we're working off pre-trained nets, is that I don't have a, like, theoretically, right? You could write a net that is image blob and image data plus associated metadata. But most of the things, I'm not going to sit around and retrain, retrain the bulk of the neural net on all of that stuff. So what we've opted to do instead to get things running quicker is that we just, the neural net is naive to lat long. But after it comes back in, I actually have that telemetry data, and I actually readjust the weightings that come out of the neural net such that like we adjust for that. So like if we are 100% certain that we are over Iowa, like the chance that it's actually water is very, very low. So there's just basically a fudge factor that says if you're over land, like disregard this to this extent.
Have you thought about pulling down Foursquare or Google KML data to make a very large labeled corpus of images and then place names?
We've thought about it. I can't say a whole lot more than that. I mean, the other issue of it is, right, like if you train, why would you train a classifier that would be wrong some of the time on these things when you can just rectify and then you have the actual geoposition and then you can actually dead on know for certain what's in that image. And so like it's sort of a, you only want to use the neural net for things that you don't know. And since we can rectify clean images and get the position, we should use that instead because that's 100% all the time. More questions? Oh, come on, guys. It's fun time. It's late at night.
How did you scale that up? So if your training takes 2 days, how did you, was there a time where you're like, okay, here's 10 minutes of data? Or how did you get to the point where you felt confident setting a 2-day job running?
I tried it a few times, and I also sort of like it is possible, right? If you have your configuration management correctly, that you can spin these things up in parallel. Didn't really do that. Like the way these things will generally work, right, is that your accuracy is going to continue. Like you want it to go up, right, over time, but it's going to reach a plateau and it's going to sort of shimmy around. And there might be some variation as it's going up. But what you're really checking for when you're getting, like, trying to set your hyperparameter as well is, like, after a couple hours, is the thing improving? Because, that's what you want. Now, there's probably another layer that we haven't quite gotten to, which is really drilling down on that stuff. But we've gotten something that's in the neighborhood that we think is approximate. We might eke another 0.5% of performance out of it, but not that much. Not with this data, not yet. We do provide all the data that we collect for humanitarian relief projects. So I think the most recent one was a big, I want to say it was a landslide in Peru. I believe was the most recent one that we is if there's a very big humanitarian disaster, we try to rush and actually get all that data open source for humanitarian relief. There was this super cool, we found all these illegal gold mines in Peru, which is like, you're like, we actually saved the world. We're not like a lot of other stars. We actually are saving the rainforest, which is like the coolest thing in the world when you actually find these guys. And then you get really good at seeing illegal miner operations too, and you filter through all the images, and you're like, wow, we actually could maybe do all this from space and find them all, which is like one of the really exciting things. I've only been in the Ed Planet for a few months, but that's like the really, really exciting stuff, is that you could actually solve that problem.
What sort of CPU instances have you found to be the best for this?
No, so I'm running just on a, I don't need the big honker, so I've just been using the smaller GPU instance. It's not the most effective. We've set up a larger GPU box in our basement, but I haven't been running off of that. But yeah, but generally, like, performance of a GPU versus a CPU, like, get a GPU, like, your time is worth that much. Question?
Do you take images of countries that don't want you to?
We image everything. There's no all set. There's very few. I don't think there's anyone, and that's not my domain. That's sort of a legal domain. But I believe that we image everything, and everyone does.
Do you have thoughts on mitigating human error in generating the training labels?
Yeah. So this is actually one of my biggest problems right now, right? And I know it myself because I eat my own dog food. I turk my own images, sort of thing. The prescribed way, right? Have you guys ever seen one of the sort of ImageNet, or sorry, there's a, what do you call it, a CAPTCHA, right? Where it says, like, click on all images that have trees, or click on all images that have signs, right? You're actually doing the turking for somebody. And what they usually do with that is that you have multiple turks going through, and you make sure that they all say the same thing. I haven't quite gotten to that point, because I just needed to generate enough data set to sort of bootstrap stuff up. But that's actually something that's coming up on the horizon, is going back through everything we've ever seen and getting like 2 or 3 sets of eyes on it. The interesting thing about that, though, is it does become easier once it's already labeled, because it becomes this, I'm going to show you 40 images or something of that nature. Actually, this may have come up right now. Oh, nope. I've shown you 40 images of a scene. Click on the one that is not correct, like which of these is not like the others, and then we can filter that out as quick as possible. So hopefully down the road we'll double check that all this stuff is good. I actually think my accuracy is getting to the point where I'm finding these things and we need to sort them out.
Have you tried Scikit image to do the
Oh,
comparison of the turking and the image data?
not yet. I mean, we use it. We use bits and pieces of it for stuff here and there. So it's a tool. I haven't. Mostly I just rely on sort of the Elasticsearch metadata and the metadata.
Yeah, I'm talking about actually, like, you've got the turked data, so you've got multiple people who've looked at it using Scikit image to actually look at okay, this is what I think is a cloud.
Mm-hmm. I mean, you have to pull out, all of that stuff ends up being like pulling out features, right? Like, what is this, what in our eye tells us that a cloud is a cloud? And that's a really hard question to answer. We know partially that it's, generally white, but not always. It's generally fluffy or long. There's different kinds of clouds. So actually the next step after this is I'm probably going to look at how do we identify all these different kinds of clouds, because we can actually tackle different kinds in different ways.
Have you ever considered using mechanical turk for this?
Yeah, I've considered it, but we have a tool. It worked well enough. It was like, the tool is actually going fast enough that, like, to get 40,000 images is just more or less like me and somebody else doing an hour a day. Like, you go get your coffee, that morning where you're just like, okay, coffee, go through some scenes.
What about stacking images from the same scene on top of each other and eliminating clouds that way?
So there's actually a step in the process. You can't eliminate. I mean, we could theoretically do that afterwards. If a scene does rectify, we generate cloud masks from that. So the cloud masks, if you know where something is, right, and you know roughly what the ground looks like, you can pretty much guess what a cloud looks like, and you can say this is cloud. Eliminating clouds is something that more like a mosaicing team would handle. All right. One more?
What's the most challenging part of this whole project? What tips do you have to make that?
I think the most challenging part was just learning someone else's infrastructure. And it takes a little bit of grit, and you just sit down and you lay out each part and you say, like, what is the quickest way to get this thing done given what's already here? And just figuring out what's there, because sometimes you have to find the person that knows where the bodies are buried to go and actually, like, make sure something's going to work. Yeah. More?
So you're saying you're coming up with a new model every week.
Mm-hmm.
Can you tell me a little bit about what this process looks like over the course of 3 months or 9 months?
Well, so it's a little bit of adding, so as like flocks of satellites come in, we have to give them more data, representative data of like scene safe scenes. So when we shoot a satellite up into space. There's a whitelisting procedure, right? So they turn on, they make sure it's all charged up, they make sure everything works. And it kind of images for a while. We get all our images cleaned up. And so part of that is like as new satellites come in, making sure that those satellites are fairly representative in the data set. That's why I'm actually looking at the distribution of images over satellites and what they're getting. And, that's part of it. Catching scenes that we've never seen before. Because as the satellites move, they kind of spread out. So there's areas, especially in higher latitudes, with our newer orbits that we haven't caught before, like, say, Greenland or the ice caps. And so that's just new data that I need to deal with. And we catch it sort of in production, and we, train the nets off that. Okay, one more.
What algorithm did you use for the gradient descent for the neural network, and how did you set the learning rate?
Learning rate was what I like to call, setting a learning rate was what one of my professors calls graduate student descent, which is I tried it, I saw if something was learning faster or not, and I adjusted it as I saw. As to the gradient tuner in there, I'd have to look. I'd have to go look at my solver file. But that's actually why I go and zip all that stuff up together and archive it, such that I have traceability into that every time we go.